Greetings, class. This video segment is all about discussing a special type of probability distribution called sampling distributions. If you haven't yet read Chapter 7 in SPATs, you might want to stop this film now and go ahead and read that read that chapter in its entirety before going on. But assuming you've read Chapter 7, Chapter 7 introduces you to sampling distributions. Now, you spent the last week or more working with the normal probability distribution, and that is a one type of probability distribution, and you used the normal probability distribution to solve a number of problems as they relate to finding area under the curve, finding the relative probability of certain events and things of that nature. And in reality, that's pretty much what the use of probability distributions is all about. However, there's a couple of very important things to keep in mind. One is that the normal probability distribution is completely and perfectly normal, meaning it is based on what's referred to, and I mentioned this briefly in one of the YouTube clips from last week or a couple weeks ago. It's based on an infinite number of trials, meaning it's making a couple of assumptions. It's assuming that we have access to all the information that we're interested in about a particular phenomenon. And it's also based on the assumption that that phenomenon is distributed normally. And when we talk about something being distributed normally, I have my marker handy. When we talk about something being distributed normally, we're talking about this is a very important thing to keep in mind. We're talking about that phenomenon being distributed in a bell-shaped curve, a normal curve, and also there being, the vast majority of that distribution being encompassed or accounted for by 3 units of standard deviation, either way around the mean. That's what it means for something to be distributed normally. It follows a bell-shaped curve, it's normally distributed, and once we go 3 standard deviations out from around the middle, we've accounted for almost all of it, like well over 99% of it. Sampling distributions are a little bit different in that sampling distributions are a very specific type of probability distribution based on a couple of things. Based on a particular statistic, and the first statistic we're going to work with is one that you are hopefully familiar with at this point, and that is the mean. So sampling distributions are based on a particular statistic, and sampling distributions are also based on the assumption that a particular statistic is based on a specific sample size. Now, what does that mean? Well, I have what I refer to as Exhibit A, and I've posted this on Blackboard, and I've called it Exhibit A. So if you don't have this handout, you might want to grab a hold of it before you continue. But I'm using this simply to demonstrate in a relatively crude fashion how a sampling distribution is built. And I want to point out at the beginning, or at the outset of this demonstration, that I'm referring to the sampling distribution for the statistic that's known as the mean. Okay? So if you're looking at Exhibit A, you see this largish circle right here with a lot of people inside. Let's assume that each one of those dots represents a person. And let's say that I wanted to build a sampling distribution using the mean and a sample size of 8. Okay, so in other words, n is going to equal 8 for my sampling distribution. So again, do you see there's a lot more than 8 people, assuming that each dot is a person. There's a lot more than 8 people in this population. Let's just pretend this is the population. This is all the people that meet a certain criteria. I'm going to build a sampling distribution for sample size 8, n equals 8. Now, how do I go about doing that? Well, the first thing I need to do is to understand what random sampling means. And if you've read Chapter 7, you know that random sampling, or something that is randomly drawn, meets a couple of criteria. One, for a sample to be completely random, every single case or every single member of that population has to have an equal chance of being selected. All right, so that seems only fair. There has to be an equal chance of each member being selected. Number two, each combination of cases is possible. Both of those criteria need to be met. That every member of the population has to have an equal opportunity to be selected randomly, and every single combination of cases is possible. And what the second part of that means, every single combination of cases is possible, what that means is that the selection of any one case is not dependent on any other case. Independence, and generically speaking, when it comes to statistics, that refers to the property of independence, that the cases are not only equal regarding the likelihood they're going to be selected, they are also independent of one another. So selecting person A doesn't mean you automatically or have a higher likelihood of selecting person B, for example. So one of the things that we need to think about before going on and building this sampling distribution is the concept of replacement. So what I'm about to do is describe in a relatively crude fashion, I'm going to describe how a sampling distribution might be built. And I'm going to do that by the following. I'm going to draw a random sample of 8 cases from this, or at least I'm going to imagine that I'm going to draw, and I'm going to put some marks on this page to demonstrate that. So imagine, if you will, 8 members of this population being drawn randomly. Just 8. And then once those 8 people are drawn, we're going to calculate their mean age in years. All right? This is somewhat of an imaginary exercise, so I'm going to say that again. Imagine drawing 8 people from this population randomly, so n equals 8, and then calculating that group of 8, their mean age. And then we're going to replace them back into the population. So that means sampling with replacement. So we're going to draw a sample of 8, calculate their age, throw them back into the pool, randomly draw a second sample of 8, calculate their age, throw them back into the pool, randomly draw a third sample of 8, calculate their mean age, throw them back into the pool, and so on. So, for example, it's going to take me just a moment to draw this, but each one of the circles that I'm drawing on this page, which I will show you in a second here, represents a sample of 8. So imagine, if you will, I just did 4, just 4 samples, just 4. So each one of these samples, and I just want to make a note on this as well, n equals 8, n equals 8, n equals 8, n equals 8. And so again, just 4 samples. So for example, I drew a sample of 8, calculated the mean age, and threw them back in. Drew another sample of 8, calculated their mean age, threw them back in. Drew another sample of 8, calculated their mean age, threw them back in. Drew yet another sample of 8, calculated their mean age, and threw them back in. And if you look very closely, I hope it comes through on the film, I've put a subscript. Mean sub 1 means it's the mean for my sample number 1. Mean sub 2 is the mean for sample 2. Mean sub 3 is the mean for sample 3. Mean sub 4 is the mean for sample 4. Now, that's just 4. Imagine if we did that forever. Imagine if we had, an infinite amount of time and an infinite number of resources and could continue on and doing this forever. So we had ultimately an infinity number, or if infinity is kind of tough to wrap our heads around, just think about an incredibly large number like 100,000 samples, all of size 8, or 1,000,000 samples, all of size 8. All right, so think about that for a minute, and then move on to the next clip.